of the presentation today, as you can see on your screens, hopefully there's no issues with that, is end-to-end flood early warning systems, or FEWS, as the acronym goes, FEWS. And Dr. Curtis will be talking about what end-to-end means, what is the first mile, what is the last mile, and what is the middle mile, and so forth. I will not try to steal his thunder, by no means. Dr. Curtis is a friend and a mentor. I work with him at West Consultants, so he is a fellow colleague. And over the few years that I have known him, I have come to respect him greatly and rely on his advice. And so, Dr. Curtis, we are very pleased to have you here and host you here in the great state of Texas. No stranger to you, I'm sure. I will read out some portions of his bio. Dr. Curtis is an internationally recognized hydrologist and innovator whose work has transformed the way we forecast floods and understand rainfall. Over a career spanning 5 decades, he has helped shape how communities prepare for and respond to extreme weather, leading everything from early flood forecasting systems with the National Weather Service to cutting-edge radar-based rainfall estimation. He was one of the first in the U.S. to deliver high-resolution, real-time rainfall data, and his methods are now used across the country to improve stormwater and floodplain management. Today, with West Consultants, Dr. Curtis continues to advance award-winning flood warning systems across the U.S. and abroad while supporting national efforts to integrate climate science into water resource planning. He's been honored with numerous national awards, including the 2024 David Maidment Award for contributions to water resources and information systems. Dr. Curtis' work continues to bridge technology, climate science, and community safety. Thank you, Dr. Curtis. With that, I will pass it on to David to get on with the presentation. Thank you, everyone, for your patience.
Thank you, Ramesh, and thanks to everybody who are joining us today. Just a quick glance at the folks that are attending. I can see it's not just the Dallas area that's being represented, but it looks like there's representatives from around the country. So that's exciting. As Ramesh mentioned, we're going to be talking about flood warning systems and in particular the end-to-end concept that was promoted years ago by the World Meteorological Organization as they give guidance to countries around the world on how to develop flood warning systems. Now, the World Meteorological Organization is kind of a specialized agency within the United Nations that's responsible for promoting international cooperation in atmospheric science, climatology, hydrology, and geophysics. And so they have conceptualized the flood warning process as what they call an end-to-end hydrologic value chain. And they conceive it as a component of threat detection. You need to find out what's happening, what's developing, and it might be a threat to property and lives. Taking that information, modeling it and forecasting potential results, disseminating warnings, having some sort of decision support system to figure out what to do next. And a really important thing is the response, the community response to those warnings. Quite often, the threat detection component is known as the first mile. Ramesh just introduced that phrase a minute ago. And at the other end, the last mile is the response to the warnings themselves, the response to the communities. And then the things in the middle are really the middle mile, and that's important as well, but they tend in many respects to be the easier part to deal with. It's the first mile and the last mile that are really, really difficult. Just to give you an idea of what the World Meteorological Organization does, it's coordinating data acquisition around the world amongst all the countries in the world that are participating in the program. And there's an unbelievable array of data sensing platforms in orbit around the Earth, platforms that are flying through the atmosphere in planes, and things like dropsondes, which are measuring the vertical profile of constituents in the atmosphere, weather balloons, and so on, and a whole variety of things at the ocean surface with buoys and ships and land-based platforms. When you put them all together, you can see how many are distributed around the world, and each one of those data points is contributing and being assimilated into the global weather models that are primary predictors for the business that we're in flood warning. Each day, 33 million observations are assimilated into the global weather models on a daily basis. That's a tremendous amount of data and coordination from around the world. And it's a huge lift to get that done in time. And it's essential for accurate weather forecasting. With that information, we need to be prepared for what's about to happen. So flood emergency preparedness really consists of an entire process. At the top is plan. If you have a threat that you know about, the flood threat in particular, you need to plan on how to mitigate it. You need to do that ahead of time. You don't have time during an event to do that. Once the threat is recognized, make a forecast, it's disseminated, and the public needs to respond. Once the flood passes, you begin to recover. Then we ask questions about what just happened and why, reassess, update the plan, rinse and repeat, start the process again. Looking at it in a slightly different way, we see here on the right-hand side of the screen is a flood hydrograph, the rise and fall of the water elevations. And I have it broken up in a kind of an abbreviated version of the planning and flood threat recognition components. The primary objective of a flood warning system is to move the timelines for planning and threat recognition forward in time. So we're moving to the left, we're getting more time, we're detecting the flood threat earlier, and we move our response earlier in time as well. So we get more time to actually respond, protect lives, and mitigate the flood damage. A really key component of thinking about that, we go back to a lot of us on the call are engineers and hydrologists. And then when we were in university and even in our jobs, we primarily focus on accuracy. Some of us sweat bullets over figuring out how to get our water surface profiles and computer models to match high water marks down to the hundredth of a foot. Well, that's only a part of the problem. And in many respects in flood warning, it may not be the important part of the problem. Really, the essential thing is the addition of timeliness. So we have to have both accuracy and timeliness in our forecasts. So the accuracy has to be good enough to be credible consistently over time, and then they have to be given to people with sufficient time to actually respond. Those two concepts, accuracy and timeliness, are in conflict with each other. Most of us are making decisions. We want more and more data, which make a more accurate decision, but that takes time. That time is taken away from the timeliness or the amount of time you have to actually respond to a particular event. So it's a real battle to balance getting enough accuracy to be credible and leaving enough time to actually respond to the event. Another key point. If you are in the flood warning business, you're in the business of making life and death decisions before you know all the facts. Case in point. I have my hydrograph here in the upper right-hand side of the screen. And way out here at the end of the hydrograph, you see 100%. That's when I'll know everything there is to know, pretty much what's coming out of that watershed. But if I wait to make a forecast at this point, well, the flood's come and gone. So the forecast isn't timely and it has no value. Might have been totally accurate, but so what? So I need to back up further in time. So if I make if I say, look, wait till I get 40% of the information. Well, that's really about the peak of the hydrograph, and that's not a very good or a very valuable forecast either. What I really need to be doing is moving it forward in time at at which times I'm only looking at maybe 5% of the information that I'll know eventually, or far less. So it's a real tricky balance to get far enough ahead of the curve to actually be valuable in terms of the forecast that you're providing. And then think about this. Floods, especially the big ones, are rare. That's like by definition. So we build a flood warning system, and then what happens? We wait, we wait, we wait some more. And in reality, the flood warning system may stand for years or decades at a time and really not be exercised. Yet when that happens and the flood finally occurs, flawless execution is expected. That's perhaps the greatest challenge facing flood early warning system managers today. If you build a flood warning system, but fail to adequately budget and perform maintenance, fail to continuously train your personnel, fail to plan for obsolescence, fail to educate users, and fail to develop public support, the system will fail, full stop. Now here's a tip. We know there's going to be long stretches of time when the flood warning system isn't used for flood warning, but the information it's collected can be useful for a lot of other purposes. So the tip is to try to develop a larger audience and be able to serve those audiences on an ongoing basis. And what happens, you develop a broader basis of support for the system. Making it multi-purpose is not a particularly difficult thing to do, because sometimes it's as simple as adding additional sensors. So for flood warning, you're typically looking at stream and rainfall, but temperature sensors are relatively inexpensive. So they can be added and serve other functions like agriculture, long-term data acquisition for design standards, education, even forest management, for example. Now we know that a major disaster occurred in hill country in Texas in July of this year. I'm going to be talking for the next few minutes about another flood warning system that was born under similar circumstances. In the Chehalis River Basin, they had catastrophic major floods in 2007 and 2009. A local flood authority was born to help solve the problems, and they resolved basically to be proactive as opposed to being reactive in case another flood occurs or when another flood occurs. The Chehalis Basin is located about halfway between Portland and Seattle in the Pacific Northwest. It's about 2,700 square miles in size, fairly low population of about 175,000 people. The really big deal is the I-5 corridor between Portland and Seattle. I-5 runs the entire length of the western United States. It is a key economic corridor, and it can be flooded for days at a time when the Chehalis River is at major flood levels. Snow is not really a problem in a basin in terms of the big snowpacks that you would consider like in the Rocky Mountains or the Sierra Nevadas, but snow can be an important contributor to an amplifier of a local flood. The real culprit for flooding and the real driver is something called atmospheric rivers. In the western United States, atmospheric rivers cause virtually all of the insured losses due to flooding. That's a really important aspect. Now, the flood authority consists of a number of communities around the region, counties, cities, villages, and so on. And then the first thing they did in 2010 was do a needs assessment after they experienced the catastrophic floods of 2007 and 2009. They wanted to improve their forecasting, better monitoring, and they wanted to monitor snowpack, improve gauging, reservoir levels, release plans, and they wanted a website. Well, they did that. They got sticker shock. Where have we heard that before? So here's an important understanding when you are doing a needs assessment. Understand the difference between needs and wants. Because a lot of the things that they wanted weren't necessarily what they needed to get a system off the ground and running and being effective. And that was part of the reason for the run up in the costs. So by sitting down and looking at what they actually needed and what else they could leverage to reduce their costs was an important finding. So we basically started with a design build approach. Rather than studying the problem to death, we tried to figure out what do we need to do right now. And one of the things that we did, we talked to the National Weather Service and found gaps in the network that they suffered through when these floods occurred. They didn't have enough data, enough rain or stream gauge information. So we added 10 sites, 8 with rain and temperature, 2 with rain and stream and temperature as well. Built a website that had all the data and warning information. And another key parameter was inundation mapping. That is such a powerful visual representation of flooding that we considered that a vital thing to have. Kind of the guiding principles, it had to be cost effective. You know, this is a watershed only had 175,000 people total. They all didn't live in the floodplain. They weren't all necessarily affected by flooding. They really didn't have a tax base. So it was really important that we leverage other resources in the region to build out a flood warning system that could be effective in a large watershed. And because of the angst and the emotion that was left over from those floods in 07 and 09, there was real pressure to have something that yielded immediate benefits. So the first thing we did was looked at all the available data that we could find that already existed in a basin and figured out a way to get it into a public website. We did that in 7 days. So in the 7 days after notice to proceed, we had a website up and running that had 100 meteorological sensors reporting. And that was really the first tangible evidence that the flood authority could point to that they were making progress in addressing the problem. Now, part of the fun of putting this system together was the fact that you had some pretty nice scenery to work in. So here's an example of one of the sites. It was a rain and temperature sensor, and I believe that's Mount Rainier off in the background. So what a place to have a job. So with the Chehalis flood warning system as part of the end-to-end value chain, the first thing we concentrated on is really the threat detection. And as I mentioned earlier, atmospheric rivers were a really key component. So what do we do to figure out when these atmospheric rivers are going to hit and where are they going to hit? Well, we call upon the Center for Western Weather and Water Extremes, located at the Scripps Institute of Oceanography, associated with the University of San Diego. And they're the premier group in the world that studies atmospheric rivers. Well, one day they sat down and figured out that, wait a minute, we really need a lot of data over the Pacific Ocean to see these things as they're forming and coming on shore. Then they realized that the hurricane hunters that operated in the Caribbean, the Gulf of Mexico, and out over the South Atlantic, monitoring hurricanes, their seasons didn't overlap. In fact, the seasons for hurricane is basically the early fall and first part of, well, not even first part of winter. It ends at the end of November. After that, that's when the atmospheric rivers tend to kick in on the West Coast. So they redeployed the Hurricane Hunter aircraft to stations in the West Coast, Hawaii, Okinawa, and Japan. Now, Hurricane Hunters are an interesting breed. Basically, the Air Force goes out and finds a bunch of crazy people, stuff them into an airplane, and tell them to go fly around for several hours in the most violent weather on the planet. And while you're at it, open a hole in the bottom of the airplane and drop instrument packages out to measure what's going on in the atmosphere, turn around and come back and tell us what happened. Well, they turned out to be a really important source of information to feed our national weather or our global weather models. In fact, as these are airborne, they finish their fly through the formation of the atmospheric rivers, they're actually uplinking via satellite to the National Centers for Weather Forecasting in the US and in England. So the data is almost immediately being assimilated into the global models. Another interesting thing they do when they see these weather systems approaching, they put in, activated about a half a dozen different places along the West Coast to launch weather balloons. Now, this seems like decidedly old school. It's just a balloon that floats up in the atmosphere and drags an instrumentation packet with it, and it takes measurements of the winds, wind speed, wind direction, humidity, the water vapor in the atmosphere, temperature and pressure, and so on, and until the balloon rises to high enough in the atmosphere, it finally bursts, and then the package comes back to the ground. But it's constantly radioing the information back to the base station where it's assimilated into the global weather models. One of the key things throughout the life of the Chehalis system is outreach. And we basically put a lot of emphasis in generating public engagement. And it's done through webinars, news articles, preparedness meetings. Social media is a big driver, and user surveys to figure out, what's important to the stakeholders. And really pay attention to stakeholder awareness with frequent updates to the board so they feel invested in the process. The governor's office of the Chehalis Basin is another important stakeholder. And we develop a gauges group of a broad representation of engineers, communities, federal agencies, state agencies that have some interest in engaging in the basin, so that we basically maintain priorities on maintaining the existing system and promoting new gauge locations and new deployments as time goes on. One of the things that we actually measure is the traffic to the website. And this is a monthly inundation map website hits. And so you can see, for the most part, it's not very active. A couple of spikes, one at the end of 2015, another at the end of 2020. And that was because those were some areas or times of high water. So keep this picture kind of in your mind, because 12 years late after the installation, we got a flurry of atmospheric rivers that hit the Pacific Northwest. Each one of those arrows describes the location of where the atmospheric river made landfall. And the color of the arrows indicate the strength on a scale of 1 to 5. And the black one is a big one. That's a category 5. But most of the ones up in the Pacific Northwest were very strong atmospheric rivers. From October 1st in 2021 to the middle of January in 2022, in other words, about 3.5 months, it rained almost nonstop. In fact, if you squint really hard, you'll only find 2 or 3 days where there was no rain. Every day had rain. In fact, at this particular station had 90 inches of rain in that time period. So what happened? It flooded at the end of that cycle. Why? Obviously, the antecedent conditions were very wet. Watershed was primed for flooding. There was significant snow on the ground that added several more inches of water equivalent that was ready to melt when a heavy rain driven by a category 4 atmospheric river showed up. That produced a lot of runoff and set many of the rivers in the region and the watershed to record or near record levels. Among the things that we tried to do with the system was create a lot of visualization tools so that people could actually see and get context with where the water is, how high it is, and a level of the threat. Here we have a cross section of one of the one of the rivers at a forecast point. And you can see the colored lines going from just when you want to first be alerted all the way up to what major flood stage is. Web cameras were a huge source of interest. It allowed us to see visually and confirm what was happening out along the river. These two photos were just a day apart. So you see the water was rising, getting near bank full. 24 hours later, it was a huge, huge event. Now, getting back to the usage statistics again, you can see from when we started flood warning or the maps in 2013 through the beginning of 2022, not a lot of activity. And then things spiked in January of 2022 to over 80,000 hits, almost 4 times the previous highs. A lot of the traffic that was driven to the website was helped by articles in a newspaper, the Chronicle, and also their Facebook posts. And here's an example of a Facebook post by the newspaper showing inundation maps, and a similar post by the Washington Emergency Management Division posting. But note how many of these posts were shared. At the time of the Chronicle, the screenshot of the Chronicle post had 388 shares and 110 shares for the Washington Emergency Management Division. This indicates a lot of engagement and a lot of interest. Kind of in summary, the website got 25,000 unique user logins in the first 10 days of January. The inundation maps were hit 73,000 times in just 2 days, January 6th and 7th. A lot of that driven by the third-party posts. Now, bear in mind that the population in the basin is only 175,000. So these kinds of metrics and statistics show that there was just tremendous engagement throughout the event by the community. Another program that's proven to be very, very popular is what we call high water alerts. And they actually subscribe to alerts for each one of the forecast points or stream gauges in the basin. And you can see that we now have 4,915 as of a day or two ago subscriptions to alerts for high water notification in the basin. User surveys have been an important part to kind of find out what works, what doesn't work, and make plans for the future. So the one question, why sign up for the high water alerts? Well, in 2007, we were caught unaware. Our house was flooded in 96 and 07. The additional information equals peace of mind. They might get flooded, but at least they know what's going on and they can make preparations. School superintendents actually care about safety of their kids. They need to decide when and where they can travel during a potential flood event. Same with apartment managers. They wanted to keep their tenants informed and ensure that they were safe. Inundation maps are an extremely powerful tool to visualize when and where the flooding is going to occur. The website actually allows users to scroll through the entire National Weather Service forecasted hydrograph and literally watch the inundated area expand and contract as the flood moves through the region. So getting back to the value chain, and really the important thing is the response to warnings. One of the things that was done after the 2007 and 2009 floods, or what happened in the floods, was that the ag industry suffered tremendous losses. Hundreds of cattle were lost, food supplies for the animals, farm equipment destroyed during the flood event. So a simple solution that they constructed were these critter pads. Farmers got their bulldozers out, moved land around a little bit, reshaped it, created some high-level spots that they could get the animals to, get their farm implements to, with knowledge that there was a flood coming. So these have turned out to be very, very successful. Individual house flood response plans. So here's an example of one homeowner. His home and the outbuildings are in this yellow box. And the current flood elevation is depicted on here is at the elevation 2002 approximately. At 2003, or excuse me, 203 elevation, this whole area is covered with water. Not over the tops of the roofs, but the houses get flooded. So this person was able to figure out with the inundation maps that we prepared when the property access was blocked due to high water, when water would get into his outbuildings, and when it was near the top of his house deck. So he had a whole plan of action on what to do. Move things that would float away to higher ground. He had a lot of firewood. He secured that. And he had a boat ready in case he needed to get out. Another important aspect of what's happened over the last decade and a half with the Chehalis is a number of master plans that were created. The latest one in 2003. Now they're doing them about every 5 years. So in 2003, they identified critical updates that were needed. There were some low-cost enhancements that were identified that could be adding new gauges, improving the high water alert messaging, and so on, improving social media. Some other important updates were some technology upgrades, gap-filling rain gauges, and so on. And then some strategic initiatives were coordinating with regional partners like the National Weather Service to improve forecasting on their end for inflow forecasting for the Skookumchuck Reservoir and improving forecast in the lower 50 miles of the Chehalis River, which is tidally influenced. And today we have over 350 sensors that are in the system, and probably 2/3 of the sensors are actually owned and operated by other agencies. So that's money that the Chehalis Flood Authority didn't have to spend, but they leverage professionally installed and maintained systems operated by others. So the Chehalis critical keys for success include the following. There's a serious maintenance commitment, ongoing and continuously. A commitment to update technologies as they can, make small incremental improvements every year, engage the public, perform user surveys, deal with the gauges group, broaden the audience, and then frequent stakeholder awareness updates. So an integral part of the preparedness program in the Chehalis Basin is really centers on what I call unrelenting outreach. It's like you don't have to bang the drum loudly, but it's really important to bang it consistently. So at the end of the day, the same process can be applied to all operations and to all flood warning systems in Texas. You have, and to be successful, really have to understand the whole process from end to end. It's been proven the same approach that's being used in the Chehalis, similar approaches in for example, Harris County in Texas, Charlotte Mecklenburg in North Carolina, Maricopa County in Texas. Just some examples of others that have followed this same pattern. And if you do that, you really may have the opportunity for some successful outcomes. And I thought this rainbow the picture that I took in August 27th, just 6 or 8 weeks after the flood, really to me signifies hope for healing and hope for recovery in the future. And if we all take a consistent approach to flood warning systems, avoid the kind of tragedy that occurred in the Hill Country this year. And with that, I'll be happy to take any questions or anything that showed up in the chat. Ramesh, you're muted.
That helps. Thank you. Folks, if you have any questions, please type them into the chat and we'll do our best to get them to Dave so he can answer. And while we're waiting, Dave, I have a question for you. What do you think, and this is a tough one, maybe you could split it up into, answer it along the way, but obviously most of us that have registered for this webinar are in Texas. And we're asking ourselves, having listened to your success story in Washington State, what are the key lessons that you think we can take from the Chehalis experience that you think we should take for installing flood warning systems in Texas, which I imagine there'll be a lot of those installed in the coming years?
Well, it's actually pretty simple. The folks in the Chehalis and other areas around the world that have had similar situations, they made a commitment not to be caught unaware again. Pure and simple. And they basically made a long-term commitment that they needed to put in the kinds of infrastructure so that they had information early and often. And they figured out what to do with the information once they got it. And most importantly, reached out into the communities and worked hard on the community response thing so that when a flood comes at 3 o'clock in the morning, they know who to get the information to, and the people know what to do with the information and hopefully have enough time to execute.
Sounds good.
Ramesh, do we have questions in the chat section?
Yes, please go ahead, Yangbin, if you want to, or whichever. Oh, I see.
No, this question for Dr. David.
David, you want to monitor and take the questions yourself, or do you want me to read it out? It might be better for you to just go direct.
All right, let me check. Okay, we had to going down, starting from the beginning, and so there's a lot of administrative stuff in the beginning.
Correct. You can start with Fatima's question.
So somebody, we frequently receive flood watch alerts on our phones nowadays, yet we rarely take action. How can early warning systems be made more effective so that people take it seriously? In the bigger picture, who is responsible for taking action when the alert is issued? That's that's really key for the individuals themselves. The problem we have right now in a lot of cases with everybody gets the information on their phone, you kind of get warning fatigue. You see them all the time. You personally don't get affected by it. But once you've been affected and suffer a loss, you tend to pay attention very closely after that. But if you haven't ever done that, sometimes it's just hard to get over the hump to realize the seriousness of the problem or understanding that it could happen to you. A lot of the activity in responding to a flood warning system or any sort of flood warnings, people hear the message, then they go ask a friend or neighbor what they're going to do or what their relatives are going to do. And it sort of becomes an ad hoc type of response. So in those cases, there's generally a lacking of public education and public engagement with the issue so that more people understand what needs to get done. I mean, I just saw a presentation about what happens to motorists when they see water over the road. And a really big driver of making a decision about whether to drive across a flooded roadway or not, as if the guy ahead of you made it through. So if somebody made it through, said, well, I can do that. You know, that's not always the case, and especially when things rapidly rise. So it's just being able to be aware and be educated as to what could actually happen. All right, so the question about the first mile, last mile. Can you elaborate on the data acquisition process in the first mile or threat detection? So there are various types of instrumentation and telemetry that can be used to inform stakeholders about flooding. Well, a very common system in Texas is something called ALERT. ALERT stands for Automated Local Evaluation in Real Time. Cities like Dallas, for example, and Fort Worth, Harris County, all have these types of systems. And they're basically radio reporting. So you have a sensor. It's something called a tipping bucket rain gauge. A tipping bucket rain gauge is if you kind of made, like with your thumb and forefingers, you can kind of make a V. There's a bucket on either side, and the bucket fills and tips. As soon as it tips, it turns on a battery-operated transmitter, sends a signal into a computer where it's recorded, and the information is placed on a dashboard. The accumulation of rainfall is being monitored, and you build up a record of whether or not you have enough rainfall to generate some sort of flooding, for example. So that's generally kind of what happens in the cities that I described, or any flood warning system. The pros one of the pros that of the alert system, this tipping bucket rain gauge concept in there. And the reason that that's important, in Texas, you're known for big thunderstorms with very intense rainfall. Those alert style rain gauges basically have a data reporting rate that is directly proportional to the intensity of the event that you're monitoring. So if really intense rainfall is important in Texas, it's really nice to have systems that the harder it rains, the more data you get. And that's exactly when you need it. If it's not raining, you're not wasting time and energy collecting zeros. So that type of technology is really valuable in a state like Texas with the kind of climate conditions and thunderstorms that you have. All right, what else? Was there a modeling component to the Chehalis system? Yes, actually. The primary modeling during the forecasting piece is done by the National Weather Service with their in-house models. The maps were created using HECRAS to create the maps and tie them into various stages at locations throughout the basin. What's really kind of interesting now with the National Weather Service, they're basically doing some inundation mapping on their own to at least give you a crude understanding of the magnitude of the flooding and where it's going to be flooding. And this is done through the National Water Model. One of the aspects of forecasting, if you're forecasting for a point, it's usually at a river gauge. Well, nobody lives at a river gauge for the most part. What you really need is to be able to relate the stage information at a gauge location to your neighborhood. Or in the case of that homeowner who had a flood response plan tied to the inundation mapping. So he knew what the gauge reading was. He could relate that to the area that would be inundated at that elevation, and he could make the appropriate response to save property in his location. And one that's a Yangbin says, my understanding is that the inundation mapping needs to be live to be effective warnings. To balance the accuracy and timing, how accurate does a live inundation map need to be? Okay. Actually, the inundation mapping doesn't need to be live in the sense that you're running a model in real time. Most of these systems have libraries of inundation maps that have been done ahead of time. The value in that is that hydraulic models, especially the RAS models, both 1D and 2D, take a long time to run. They can. There are other technologies out there that do things faster. And they're also notoriously unstable at times. And you know when they're going to be unstable? At 3 o'clock in the morning when you need the data. And you need some expertise locally to be able to run the models at 3 o'clock in the morning. And that's not always available. So the safer way to do is to establish a set of maps ahead of time that are ready to go at a moment's notice. Now, how accurate does it need to be? When you think about emergency response, quite often the emergency response plan has basically a small number of divisions, small, medium, and large floods. That's all the manager cares about, because all he knows, if I'm going to have a small flood, I do X, Y, and Z. If I have a medium flood, I'm going to do these 3 things. If I have a major flood, I'm going to do these things. They don't care if you give them a map that's accurate to 1/100th of an inch. Doesn't matter, because they're basically making much broader decisions than that. And so you basically just need the kind of information that the emergency management and their first responders need to effectively initiate the actions that are already in their plan. Another question, are you aware of any examples or opportunities using sensor data to inform public evacuation routes that they can communicate? Yeah, actually, there are a number of websites that departments of transportation use that indicate where the roads are closed. The Chehalis system, they could actually, the Washington State Department of Transportation uses the forecast to understand when Interstate 5 is going to be flooded, and they put out warnings about that. More and more cities, like Dallas, for example, and the North Texas Central Council of Government area are looking at roadway flooding systems so they can keep the public alert to developing flood events. There's more and more communication with GPS systems in your car, for example, like Waze. Fort Worth is working with Waze to get information into your car of what streets are being flooded. Excuse me. What else? And so we have downloads. We got links to the Chehalis system. Okay. Yeah, there was a comment about the accuracy of flood warning systems is critical, and you need it to establish trust. That's really important. And a lot of this has to do, flood forecasts are going to be wrong. That's a given. Because you're making flood forecasts before you have all the facts. So what you really have to do is continually educate the public about that. So they begin to understand the reasons why and begin to appreciate what you're doing and the kind of information, how to use that information to effectively manage their own lives and situation. And I think that's all I have in the chat at the moment.
Dr. Curtis, that last question/comment really brought it home, didn't it?
Yeah, it did. It really speaks to engaging the public continuously. What I call the half-life in interest in flooding is pretty short after you've had a big flood. So it takes a real commitment to manage that process and engage the public in every way you can. And it's just little reminders. It can be a notice in a utility bill. It can be a booth at the fair, the county fair in the fall. educating in the school system, letting the kids know. So there's just a lot of really low cost things that can be done that promotes engagement throughout the year. And they begin to understand what's going on, and they can make these assessments of, and you build credibility to do that. So
Yeah, I really see this, the success of flood warning systems as a public-private partnership of sorts, where, you know, a more aware public is a more safe public. And can't always blame technology or public agencies for dropping the ball, so to speak. And I think that was sort of, to me, the most important aspect.
and you have to be willing to do it for the long haul. Like I said, the big floods are rare. So you know you're going to have long periods of time where the flood warning system is not going to be really exercised. So being able to kind of constantly make people aware of the site, put useful information out there that maybe serves other audiences that they can access it. So the more you drive traffic to your website, the more people understand the website. And when the time comes where they need to use it in a hurry, they're not fumbling around trying to figure out where everything is. So it's another real important aspect of it.
All right. I think it's time to end this webinar. Thank you. Thank you, Dr. Curtis.
You're welcome. Thanks, everybody.